Hi there. My name's Randy Bryant. I retired from full-time faculty about 2 years ago, but since then, as an emeritus faculty member, I've been very active in research, writing papers, working with students, getting grants, and so forth. And so I consider myself still a full member of the CMU faculty. Let me tell you about some of the work that I'm doing research-wise. Most of my career has been spent on some types of automated reasoning programs, by which I mean we take some formalized description of a problem and try and describe some properties of that system. An example of this tool would be a simple Boolean satisfiability solver, or for other forms of logic, or even verification tools such as model checkers that try to prove the correctness of some class of systems. There's a problem with the way we've implemented these tools historically, that we can't really be sure that the code is correct. In fact, there's a pretty good chance it's buggy, given how large and complex these systems can be. And so that always has produced in the back of my mind a concern. We say we're formally verifying this or that, but we're really not sure if the results that we're producing are correct. And so what does that mean for formal verification? Well, some people have suggested and actually successfully implemented reasoning tools in a theorem proving framework, and that's a very impressive activity. But these tools are, first of all, very difficult to develop, and second, tend not to be able to scale up to the range of problems that people are really interested in solving. So another approach is to say, well, I can't really verify the tool, but I can verify individual executions of the tool. And so what we'll do is require the tool to not only produce some answer, but also to produce a checkable proof that its answer is correct. And we'll do this in some type of framework such that these tools, these proofs can easily be checked, even if they're very large. So you might think, well, you've just pushed the problem down the road to say you've got a buggy reasoning tool, and now you can provide a buggy checker, right? Well, not quite. First of all, think of the reasoning tool as orders of magnitude more complex than the checker. And in fact, it may be possible to produce a formally verified checker. And so now we can be sure that if our tool produces some result and we've generated a proof and that proof is checked, then we've in effect formally verified the outcome. And that's a very powerful result. It means even if we discover a bug in the tool later, we don't need to rerun those old results. They're solid. And it really transforms the experience you have in using tools like this when you can have that certainty of the checkable proof. So that's sort of the general area of research that I'm working in these days. And it manifests itself in two different directions. One is in classic SAT solving, for which checkable proofs and their frameworks is highly developed. But there's some severe weaknesses in current SAT solvers, and I'd like to plug in some of those gaps. The other is to look at tools beyond SAT solving and try and produce proof frameworks and proof systems that will enable us to formally verify the results of executions of those tools. So let's look at SAT solving. We can think of it as a program that takes a Boolean formula, and if the formula is satisfiable, it will produce a solution. And so we can easily check that that solution satisfies the formula. The tricky part becomes, what if it declares to be unsatisfiable? How can we be sure that the solver has really searched through all possible solutions to this formula and detected reliably that none of them will satisfy it? Indeed, there's a lot of experience out there of people who wrote tools and they found they were buggy in this regard. So what we'll do is produce an unsatisfiability proof. And for this, as I mentioned, there's very highly developed proof frameworks and tools to do it. And in fact, it's become sort of a requirement for at least competitive SAT solvers since around 2016. The problem is that current SAT solvers do very poorly on some classes of problems, or there's some where they know how to produce solutions, but they don't know how to produce proofs. So let's take it as an example, a very simple benchmark problem, which basically states a set of n variables has both even and odd parity at the same time. This is, of course, absolutely not true. But just to make it a little bit more challenging, we'll randomly permute the variables in encoding the second parity constraint so that it's not just obviously syntactically false. And when we feed this to our favorite modern SAT solver, KeySOT, based on a class of algorithms known as CDCL, we see it does very poorly. Given 10 minutes of execution time, it can't get beyond about n equals 42. And we can see, in fact, that it's scaling exponentially. So that's not very impressive. So starting several years ago, I pulled out some work that I did many, many years ago on a representation of Boolean functions known as binary decision diagrams. And it has some very nice properties, especially with regard to SAT solving. And in particular, it has some very nice algorithms for creating and modifying and testing properties. And these algorithms can be encoded in such a way that the individual recursive steps spit out little very brief proof steps that when you concatenate that all together forms an overall proof that the reasoning by this BDD code was correct. And it does this in a proof framework that's compatible with the standard proof frameworks used by CDCL SAT solvers. And so using that same benchmark, you can see I can push way beyond n equals 42. The red lines show a use of BDDs in a very direct way, doing conjunction and quantification operation. And the green ones show using Gaussian elimination, which is a well-established technique for reasoning about parity constraints, but for which there is no known way to convert those results into a checkable proof in the same standard proof framework. And what we showed is if we sort of hang BDDs off the side, they're not actually doing the reasoning, they're just helping justify each of the individual steps of the parity reasoning, the Gaussian elimination, such that the overall result is a checkable proof. And you can see that can push up to n equals 1,000,000. So we've taken a problem that was absolutely intractable for CDCL and turned it into one that's really quite straightforward. So this diagram kind of illustrates one way of thinking about what we've accomplished. On the y-axis, we show how tractable are problems, meaning that how difficult are they from a mathematical perspective or from a practical verification perspective. And the x-axis shows how well do CDCL solvers do this. And so if we look at the sort of outer limit of what CDCL solvers can do, and the lower limit of what's considered interesting from a mathematical perspective, then we see that modern SAT solvers have started to crack open those problems and produce results that no other solution method has been able to solve. And that's really very powerful results. My parity problem, on the other hand, is not an interesting mathematical problem. It's patently false that some set of variables has both even and odd parity. But it's hugely intractable from CDCL. And so what we've done with BDDs is sort of help fill in that lower right quadrant and created a way we can produce checkable proofs of problems for which CDCL doesn't do well, but for which its proof frameworks are totally adequate. What I'd really like to do, though, is combine BDDs, CDCL, and whatever known solutions we can come up with for solving SAT, and try and produce tools that can push really interesting, challenging problems that we can't solve by any other means, while generating proofs of an unsatisfiability. So that's one area of research that we keep pursuing. And now let me talk about beyond SAT solving into classes of problems for which there aren't standard proof frameworks. And so let's look at the problem of model counting, which is roughly how many assignments to a Boolean formula actually satisfy that formula. And I'll express it in terms of a function I call rho, which is the fraction of all possible assignments that satisfy the formula. So it's clear that this is, and I'd like to be able to produce a number rho and produce a checkable proof that that's truly the density of a given formula phi. Well, looks a little tricky because this is rational arithmetic and Boolean reasoning merged together, and it's not so clear how we can combine those two in any proof framework, especially one that's easily checkable and easily automated. So our current work is to say, well, let's try and push the Boolean part of it as far as we can so that the rational arithmetic part of it is really quite trivial. And our strategy for doing this is to convert the formula into a standard, well, not a canonical representation, but a class of representations I call a partitioned operation graph, or POG. And this is a Boolean formula with the standard conjunction, disjunction, and negation operations, but it puts heavy restrictions on these in such a way that we can trivially compute the density of that formula. And then what we want to do is use Boolean reasoning to prove that this formula is logically equivalent to its POG representation. So we split this density problem into a Boolean reasoning part, transforming it into some other representation, and then a rational arithmetic part where that is over a much simpler class of problems. So this shows an example of a formula involving two clauses and one of its possible POG representations. And you can see that it uses and, or, and not, where the blue dots represent Boolean negation. But our requirement is that anytime we do a disjunction, it's over subformulas that have disjoint assignments. And so we can compute the density of the result as just the sum of the densities of the two subformulas. And similarly, and whenever we do conjunction, we require them over disjoint sets of variables. And so we can just multiply their densities to get the density of the result. And so given that POG representation and a proof that that POG is logically equivalent to the formula, we can compute its density by this very simple set of arithmetic operations involving multiplication, addition, and an operation I call tilde W, or just 1 minus W. And so we have to prove the correctness of that, but you can see it's a very straightforward operation. Whereas the logical equivalence is not so straightforward, but we can use fairly standard Boolean reasoning techniques to do that. So that work's just fairly recent, and we're still in the very early stages of it, but it illustrates some directions we're trying to go to expand this idea of checkable proofs beyond pure Boolean reasoning. So let me just draw back a little and tell you about this type of work that I've been involved with quite some years, and I still find really fascinating for a couple of reasons. One is that the tools we develop are actually important to the world. Over the years, I've developed verification tools that have been very important in both the hardware and the software domain. And even a tool like a SAT solver is a core reasoning tool used in many different venues for doing reasoning, and having those checkable proofs is an important component to this. Another is that it sort of builds on all the different dimensions of computer science, from theory to implementation, software engineering, running experiments, tuning and improving, benchmarking, and so forth. And we get to sort of jump back and forth between those, thinking about things that are fairly formal, but at other times just hacking code, making sure it runs, trying to make it run faster, and having some quantitative metric about why one idea is better than the other, and that it can actually solve classes of problems that other tools can't solve. And that's really a nice way to be able to measure results, as well as actual impact. So that sort of sums up the type of work I've done, some directions I'm doing, and I'd be glad to talk to any of you. Please get in contact with me if you'd like to learn more.